Okay, let's go over balancing redox reactions today. Now, balancing redox reactions is slightly more complex than balancing standard reactions, but it follows a relatively simple set of rules. Now, earlier when we went over balancing regular reactions, we didn't have to deal with any compounds that were ions. They were all completely free of charge, neutral compounds reacting together. But when we're dealing with redox, we're likely going to encounter a lot of polyatomic ions or compounds that have, or like freestanding monatomic ions. And we have to factor those in because they actually play a very different role when it comes to redox reactions. Now, there are two different types on how redox reactions are balanced. It depends if these are in an acidic solution or a basic solution, and based on what they are, it kind of changes a little bit on how they are balanced. So let's look at how if it's balanced in an acidic solution and a basic solution, how they differ. And today we're just going to go over in this video just the acidic solution balancing. So when we're balancing half reactions in an acidic solution, remember, you have to be able to write half reactions, both the oxidation half and the reduction half reactions. Now, how do we identify that it is in an acidic solution? Or basically, either it will explicitly be stated in the problem saying that this redox reaction is in an acidic solution, or usually a strong acid is involved as one of the reactants. Remember those 7 strong acids: hydrochloric, perchloric acid, chloric acid, hydrobromic acid, hydroiodic acid, and then we had nitric acid and sulfuric acid, and those were the 7 strong acids. Now, or if you look at certain reactions, over the yielding arrow, you will notice that a hydrogen ion is to be written. So if I were to give you a brief example, if you were to have a reaction A plus B going into a product C plus D, on top of that yield arrow, you will notice that there is an H+. Remember, in acids and bases, H+ hydrogen ions were associated with acids. All right. So how do we balance these? I'm going to go through a set of simple rules and show you along with examples. So first step is you have to be able to write those half reactions. So again, assigning oxidation numbers is a basic skill now. So using those 9 rules we went over in our other video, you should be able to assign oxidation numbers and then figure out which compounds are being oxidized and which ones are being reduced, and write those half reactions. The next step is you balance everything in respect to the atoms involved except for the hydrogen and oxygens. Notice that this is similar to when we were balancing equations from last semester. We balance the hydrogens and the oxygens last. Same here. We don't have to deal with it right away, so we balance everything else. All right? And then the next, we balance the oxygen atoms. Now we're going to deal with the oxygens first, and we balance it by adding water molecules, because most of these redox reactions we deal with in acidic solutions are in water, or an acidic solution which deals with aqueous solutions. So water is our excess that we add around. So we add the exact amount of oxygen needed on either side with water. Now, when we add that water, obviously there are going to be hydrogens that appear in certain equations that didn't exist earlier. So how do we balance those? We balance those with hydrogen ions, because remember, we're in an acidic solution, which means that we have excess hydrogen ions. So we balance it using those. All right? So notice that we have to specifically have that positive charge. So please don't forget that. So step 5. Next step is balance the charges by adding electrons to one side. Now, what does this mean? Now, we balance everything in respect to oxygen and then hydrogen. And then on depending on that, after that, we now have to deal with charges. So what does it mean by balancing each side by adding electrons? Electrons naturally have a negative charge, which means when you add up the sum of the reactant side and the product side, the sum of the charges have to actually equal each side. Whatever you're starting with, you have to end with the same charge. And if they don't, you have to add electrons to certain size so that you can balance that out. All right, we'll see in the example what it means. Okay. Next step, balance the electron change in the two half reactions by multiplying the two half reactions by the least common multiple. So you're going to have your reduction reaction and your oxidation reaction, and you're going to have adjusted the charge by using electrons. Now, what our goal here is so that the oxidation and the reduction have the same amount of electrons that have been added or on each side. So what we do is we have to multiply each of those reactions, half reactions, by a factor so we can have equal number of electrons. Again, as we go through examples, it will make a lot more sense. And then the next step, we add the two half reactions back together. Whatever's on the reactant side, we combine them all on one side. And then whatever's on the product side, we combine them all onto one side. And then our last step, if you have same things, same compounds, exact same compounds from the left side, reactant side, and the product side, we can actually cancel them out using the same quantity. All right. And by this time, our goal is so that each side, the electrons are actually all cancelled out. So hopefully that's going to make a lot more sense as we go through this example. All right. All right. So now let's look at this example right here. We have iron 2 plus with dichromate ion reacting together to create iron ion and chromium ion. All right, so let's identify some of its oxidation numbers. So first of all, iron should have a +2, and oxygen we know for a fact has a -2, giving us a combined oxidation number of -14, which then we need to realize that the sum of these combined has to be a -2 right here. So what do? We then realize that chromium has to be a +12, but since we have two chromiums, that's going to give us a +6. And then we move on to iron having a +3 and chromium having a +3. Now, from here, we should be able to write our half reactions. Oxidation is losing electron, which means the oxidation number goes up. And we notice that iron goes from +2 to +3. So we realize that this is our half reaction for our oxidation. And then our reduction part, it's actually the chromium. It goes from +6 to +3. All right, notice those number changes. It gains electrons, so the number goes down. So we write these as our half reactions. This is step 1. All right, and then we move on to step 2. Step 2 deals with balance the half reactions with respect to the atoms involved, except for the hydrogens and the oxygens. Now, if we look at our first one, we have iron and iron. We each have one on each side. Even though the charges are different, we're dealing with the quantity of the atoms, right? So we don't have to balance the first oxidation number set. Now we look at the reduction part. We notice that we have two chromiums on the left side and we have one chromium on the right side, which means we have to balance the chromium. So we add a coefficient of 2 so that we can multiply it by a factor of 2 and equal out the same number of atoms. That is step 2. Remember, hydrogens and oxygens is not yet. Our next step, however, we now get to balance out our oxygen atoms. How do we do that? On the top one, oxidation reaction, it doesn't have any oxygen, so we don't have to bother balancing that out. But on the reduction side, on the reactant, we have 7 oxygens, which means we need to balance that out because on the right side, the product, we have no oxygen. Which means if we want the same amount of oxygen, we need to add 7 water molecules because by doing so, remember that coefficient is a factor. All right, so that tells us we now have 7 oxygens on the product side. That is step 3, balancing out the oxygens with water molecules. Our next step, we now get to balance out the hydrogens. Again, oxidation doesn't have hydrogens, so don't worry about it. And then we move on to our reduction. If you look at our product, we have 14 hydrogen atoms on the right side on the product, which means we now have to fix it by adding hydrogen ions. So if we have 14 on the right side, we must add 14 ions on the reactant side. All right? Notice we have now balanced everything in each side, except for charges. That's our step 5. Step 5, we balance out the charges by adding electrons to one side or the other. Now, we have to be careful not to make mistakes here because the coefficients actually play a big role in this right here. So when we deal with stuff here, we have to have a combination of the oxidation numbers. So if we look at our first part here on the oxidation, we notice that the total charge is +2. And then the right side on the product, we have a total charge of +3. Now, we all have to remember electrons are -1 in charge. So we can only add it to bring numbers down, which means the only side that an electron is needed for the first oxidation half is our product side. By doing so, we have an overall charge of, when we combine these two, of a +2, which is now equal in terms of reactant charge and the product charge. So we now go to the bottom half of the reaction, the reduction. We now have 14 hydrogen ions. So we have a +1 charge, but we have 14 of it. So right here, we have a +14. Right here, we have one dichromate ion with a -2 charge. So we have a -2 in charge, which in turn gives us a combined +12. All right. Next up, we have chromium ion. Each chromium is a +3, but because we have 2 of it, our total charge is going to be a +6. And right here, water has 0, even though there's 7, 0 times 7 is still a 0, giving us a combined charge of a +6. Now this tells us +12 and +6, we need 6 extra electrons on the reactant side on the bottom half. All right. By doing that, we have a total charge of -6 here, giving us a total combined of +6, which is now balanced from the reactant to the product side. That is step 5, guys. Step 6, we are now going to balance out the electron change for each half reaction. Now notice we have only 1 electron here. We have 6 electrons. We want the same number. And in order to do that, all we need to do is multiply the top oxidation reaction by a factor of 6. Now, by doing so, we can shift the entire top part by multiplying it by 6 and distributing it. So now we have 6 iron 2+, and then 6 iron 3+, and 6 electrons. Now that we have all the same number of electrons for our oxidation and a reduction, we are ready for a final entry. Almost there now. Step 7. Add the 2 half reactions back together. So remember, the yield arrow separates the reactants and the product. Whatever's on the reactant side, we combine them all together. So we have 6 electrons, that comes from right here, and the 14 hydrogen ions. And then we have our dichromate ion, and then we have our iron 2+ right here. And then our yield arrow comes along. And then the same pattern follows. We have our 6 iron plus right here. We have our 2 chromium. We then have our 7 water molecules. And then we have our 6 electrons. This is step 2. We just combine the left side all together and the right side all together. And then enters our last step. Cancel anything out that appears on both sides of the final equations by number. So, by the end, remember the goal is all electrons should cancel out, and that's the main reason we had to do step 6. So if we look over here, 6 electrons and 6 electrons, they can cancel each other out. Now there are no other things that are equal to on the left side and the right side. Yes, we have both iron and iron, but note that the oxidation number or the charge is different, making it a completely different ion. All right, so there's nothing much more for us to go from here. So this is now our finalized answer to how to balance the following reaction in an acidic solution. All right, so this is how we balance redox reactions in an acidic solution. Hopefully this helped, and hopefully you guys can go over this and can understand the concepts of redox, balancing redox reactions in an acidic solution. Thank you.